Okay, what's up, class? So this is the second video in the module that deals with Fusion 360 simulation and specifically Skyscrapers. So the first module we learned that it took Fazlur Khan and his innovative idea that skyscrapers be designed as a single cantilever coming around to really allow us to keep building taller and taller skyscrapers in the 20th century. Okay, and that kind of design is still used to this day. That model is still used to this day. So before we understand how this is kind of used in skyscrapers, we first need to understand how actual cantilevers behave. Okay, a cantilever once again is like a diving board. It could be an awning. So basically anything that has just support on one end. And for our scenario, the load is going to be applied at the opposite end. Okay, but before we get into that, we need to understand stress strain, which is kind of the basics of all engineering that deals with materials.
Strain is a quantity.
Whoops. There we go. Stress. Nope. Is this it?
Stress and strain are fundamental concepts that are used to describe how a body responds to external loads. In this video, we'll explore these concepts using the simple example of a loaded bar. Here we have a solid metal bar that is loaded by two equal but opposite forces. We refer to this as uniaxial loading because all of the applied loads are acting along the same axis. The two forces are pulling the bar, causing it to stretch. Internal forces will develop within the bar to resist these applied forces. We can expose these internal forces by making an imaginary cut through the bar. I chose to remove the right side of the bar, but I could have removed the left side instead. For any imaginary cut like this one, the internal forces develop in such a way that equilibrium will be maintained. In this case, the effect of the internal forces acting on the cross-section created by our cut will be equal to the effect of the applied external force. I have represented the internal forces as four separate forces here, but I could have represented them as 1 or even 20 forces. In reality, the internal forces are distributed over the entire surface of the cross-section. For this reason, it doesn't make much sense to talk about specific internal forces. Instead, it is better to talk about stress. Stress is a quantity that describes the distribution of internal forces within a body. It makes it easier to discuss the internal state that develops within a body as it responds to externally applied loads. Stress is a measure of the internal force per unit area, and so has units of newtons per meter squared in SI units, and pounds per square inch in US units. Newtons per meter squared are also called pascals. In the case of our axially loaded bar, the internal forces are acting perpendicular to the direction of the cut we made. This type of stress is called normal stress. We can calculate the normal stress in our bar as the applied force F divided by the cross-sectional area A of the bar. It is denoted by the Greek letter sigma. One reason being able to calculate stresses is important is because it allows us to predict when an object will fail. Let's say our bar is made from mild steel, which has a strength of 250 megapascals. The bar will fail when the stress within it exceeds the strength of the material. If our bar has a diameter of 20 millimeters, for example, we can calculate that it will fail if the applied force is larger than 79 kilonewtons. Normal stress can be either tensile or compressive. In this case, the stress is tensile because the forces are stretching the bar. If the forces were trying to shorten the bar, we would have a compressive stress. The sign convention that is normally used is that tensile stresses are positive values and compressive stresses are negative values. In the case of our bar, it is reasonable to assume that the stresses are distributed uniformly across the cross-section and along the length of the bar. But this is a very...
Okay, and then The next video is about strain, which we started by accident last time, which kind of coexists with stress.
Strain is a quantity that describes the deformations that occur within a body. If we fix our bar at one end and apply a force to the other end, the force will cause the bar to deform. The normal strain within our bar associated with this deformation can be calculated as the change in length of the bar delta L divided by the original length L. Strain is a non-dimensional quantity and is often expressed as a percentage. Normal strains can be tensile or compressive.
Okay, and then in this example, we're dealing with something that's just in tension or just in compression, so it's a unilaxial load and stress. So basically, the whole load is acting on a single axis. This is different, or the whole stress is acting on a single axis. Our cantilever is different, and it'll be experiencing bending stress, which still has tension and compression stresses, but it's a little more complicated. So this video kind of begins to introduce that for us.
Distribution in a beam that is bending, for example, will be more complex. Stresses will be tensile on one side of the cross-section, but compressive on the other.
And so across the cross-section of the member, if you cut through it, it will be more of a gradient from tension to compression with some zero stress in the middle. And so if you're confused, what part might be in tension, what part might be in compression, tension, once again, is where the material is stretching, or getting longer compressions where it's compressing. So in a cantilever that has a load going down, the top's going to be in tension, the bottom's going to be in compression. Okay. So to kind of review this before we end this video, stress, once again, is force over area when it's a unilaxial load or unilaxial stress, a normal stress. Okay, it's basically looking at the distribution of internal forces across the body or across the cross-section. So the bigger body you have or cross-section you have, the less stress you're going to have because those internal forces are distributed across more of the member. For bending, it's a little more complicated once again. The equation is my over I. M is moment. It's force times distance. We'll talk about that in a sec. Okay, but Y is the distance from the center of mass, and I is the moment of inertia. So I kind of is similar to area in that it's a cross-sectional property, and the shape of the cross-section kind of changes area and changes I. Y is the distance from the neutral axis or center of mass. Okay, and this counts for how the bending stress is not the same throughout the whole cross-section of the member. Once again, how it goes from tension on the top to compression on the bottom, and in the middle at that neutral axis, it is 0 because Y will be 0. Okay, so let's end this lecture with what's a moment. Okay, so moment is force times distance. Okay, it's a measure of the tendency to cause a body to rotate about an axis. In our case, the tendency to bend. Okay, so the tendency to bend. It's kind of the opposite of what you would think. The moment is 0 underneath the load, and the farther away you get from the load, so the bigger the distance from the force, the larger the moment is. Okay. And so if we calculate the moments at A, B, and C, A is going to be the load times L. Okay, so the largest. B is going to be the load times L divided by 2, and C is going to be 0 if we can see it. Okay, because it's right underneath the load. Okay, so this is where we're going to stop this video, so this video doesn't become too long. But the key to remember, once again, that stress is the distribution of internal forces in a member. Strain is kind of change in length over length, so it's giving you an idea of how much deformation is going on in the member due to that stress. And then in a cantilever, there's bending stress, which means across that cross section, the stress is not the same as it goes from tension on the top, so positive on the top, to compression on the bottom, negative on the bottom. Okay, and somewhere in the middle at that neutral axis, it's going to be 0. The farther away you are from the load, the higher the stress is, because the higher the moment is. Okay, so we'll pick up on this in the next video.